Okay. Okay. Oh, yes. Yay. Cool. Okay. Maybe a few more seconds. I don't know if there's... Okay, so my name is Dom Farolino, and welcome to my final presentation. I'm glad that we got to book this room and I can woo you in this incredible atmosphere. All right, maybe a couple of minutes left. Is there anybody else? That's a no. Okay, so yeah, this is my final presentation where I'll be going over my internship this summer with the Chrome loading team. So here's a, why isn't the clicker working? Connection lost, awesome. 1 second.
Welcome to Bluetooth.
Oh, yeah, really? Right?
Yeah.
Oh, yeah. So here's a quick outline of the presentation that I'm going to give. First, I just want to start with a little bit about me and give you some background information. And then a lot of you know that my work with Chrome and the web platform extends prior to the internship. So I want to talk about some of the projects that I've worked on before joining Google this summer, before moving on to my summer projects that I did with the team here. Finally, I want to wrap up with a little bit about my life in Tokyo and some of the things that I've done, and then finish with all of you and give thanks and a heartfelt goodbye. So here's So yeah, here's a little bit about me. This is me in roughly 5 months. A lot of people think that the hair is fake. I don't know. What kind of person would my mom have to be to put a wig on her child like this? But so yeah, I'm originally from the United States, specifically Ohio, if you know where that is. I'm a master's student at the University of Cincinnati, and previously I've done internships with Microsoft and Mozilla. With Microsoft, I was on the Outlook for Mac team, where I worked on calendar events. And with Mozilla, I was working on the Firefox graphics stack. This was my first time to Japan, this internship, so I'm super happy to have gotten to spend it with an awesome team like Chrome Loading here in Tokyo. Okay. Maybe it's the distance.
It's Bluetooth, it's distance.
I guess. 1 second.
You don't want to use a real clicker?
So, do you have it? You do. Let's give this one more shot. Okay. All right, I'll just stand a little more on this side. So I want to talk about how I got started with Chrome and the web platform. So a while back, when I was primarily a JavaScript developer, I came across the GitHub profile of a guy named Dominic Danicola, and I thought what he was working on was pretty interesting. It was mostly web standards, and I was interested in how he was kind of slowly evolving the web platform. So I reached out to him and asked how I could get kind of started working on the stuff that he was doing. And so he pointed me to the What Working Group's console standard, which was a lesser known web standard for sort of beginners to get started with. I started seriously contributing to this standard and took a lot of ownership, as well as working on Chrome's implementation of the spec as well. And after a while, he eventually emailed me asking me if I wanted to basically become one of the lead editors of the spec. And ever since then, I've been pretty involved in both web standards and Chrome's implementation of such things. The first project that I started working with, or one of the first projects that I started working on, both in the standards world and in Chrome, was the refer policy attribute for script elements. So before we get into exactly what that is, let's just talk about how scripts are fetched in the first place. So say you're on a.com/cat.html, right? It's an awesome site to see your cat GIFs. And you have some script here, and to load the script, you make a request to the network, and you access the resource. And the resource comes back, the function is executed, and all your cats fly into the page, and you get all the GIFs that you could ever want. What you might not realize is how the web works is basically a bunch of request headers are sent to B.com's origin servers. One of these headers is the referrer header, which basically allows B.com to track what other sites are referencing it, so we can kind of just determine its position on the web and who is frequently consuming it. But in a world where we're trying to build a more private and anonymous web, we thought it best to give the ability for developers and therefore implicitly users to opt out of such sort of referrer tracking. And so thus the referrer policy attribute was born. This is an attribute that exists on several resource fetching HTML elements, but did not exist on script at the time. So with this attribute implemented, the developer can specify referrer policy on the script like this and give it a value that sort of mandates the shape that the referrer header will take on the request headers. In this case, we have the value no referrer, which implies that no referrer will be sent. So when the request is made to the script, the b.com's origin servers are accessed, and the request headers actually do not contain any referrer header. We've completely omitted it. So we've made a.com essentially anonymous to b.com, which we thought was an important primitive to expose to both developers and users. And of course, your cats load in a nice privacy-preserving way. So I undertook this independently from the standards point of view and committed to the HTML standard, and also submitted an intent to ship on Chromium's behalf and implemented this in Chromium. And most of the reviewers were actually in this office. So this was a really cool change for the platform because it's privacy preserving, but we also got to delete 554 lines of failed test expectations that I introduced to the code base by testing and standardizing the feature. But the main reason this feature was really cool is because, well, Keynote said it was. And that's sort of like the litmus test for like whether something's totally cool on the web and has a deserving place. So the next project I worked on, partially on Chrome's behalf during college, was preloading responsive images. So just a quick overview of how images work on the web. Generally in markup, you specify your images like with an image attribute and an image element, a source attribute, and an alt attribute if you want to be semantically correct. But a lot of times we want our images to be responsive to the viewport. So maybe we want to load one image when the viewport takes a certain size and a different image otherwise. And so responsive image syntax was born in HTML. And this allows the developer to specify basically a set of images and a set of corresponding media queries for the screen to match for each of these images to be loaded. And the browser will make its best decision for loading one of these. However, we also have this feature called Preload on the web, where we can take like an image and actually load it before we need it. So when the page eventually needs it, it's available really fast. But with the responsive image syntax, we do not have such a thing. So it's impossible for developers to really preload these types of things. And this gives the developers some pain, right? We have no responsive image support for preload. And so this ends up being a big performance loss because we're sort of making the developer choose between responsive images and preloading. And we had some interesting clients, or some clients who were interested in this feature as well from a performance perspective. Specifically, Google Search and AMP was interested in implementing this on the search result pages. So if you haven't heard of AMP, it stands for Accelerated Mobile Pages. And it's basically a product that grew from Google Search here. You've probably seen AMP results on your mobile page. Basically, if you look up something and it's got the little AMP lightning bolt, it was sort of like built with the AMP framework. It's sort of guaranteed to be fast. It loads from Google Cache. And so these search results are often promoted. And with AMP being really interested in performance, they were interested in also loading these preloading responsive images. And so the proposal we came up with was to add 2 new attributes to the link element that corresponded with the existing attributes for responsive image syntax that the image element had. And the way this kind of was born was Keynote was basically said, hey, we're working on implementing this, but we don't really have the bandwidth right now to spec it. So she contacted Adi Osmani in Mountain View and said, maybe could someone on your team or that help standardize this? And so Adi reached out to both me and some developer relations people in Cambridge. And eventually the feature just kind of sat around for a while and was unable to be shipped to the web platform because it wasn't done from a standards point of view. So eventually I found the time to pick it up during school, and I submitted a pretty non-trivial change here to the HTML standard. As you can see, it required a lot of conversation and deep understanding of the image selection algorithms in the HTML standard. And so it was a lot of fun. It was a good feature. And being such a new part of the web platform, it was actually really exciting to see that AMPS data has already recorded that over 15 million independent AMP sites were using this performance primitive. And again, those are just AMP sites, so we expect many more to be using this outside of AMP as well. But sometime in the middle of all this random work, Kiniko had asked if I wanted to come and intern with the Chrome loading team here in Japan. So I, of course, said yes, because I'm here. And then that brings us to the next part of this presentation, where I'll discuss summer projects that I worked on with the loading team. So the first project kind of revolved around preload and subresource integrity. So these are like some foreign words. I don't expect everyone to totally understand this right off the bat. So let's just talk about them independently. Subresource integrity is this feature where we let the web developer not only like load a script, but also specify some expected hash that the contents of the script should have to know that it wasn't tampered mid-flight or something like that. So the integrity attribute, the syntax is relatively simple, basically a hash algorithm, then a hyphen, and then the expected hash. So we access this resource, in this case b.com script.js. We compute the hash given the given hash algorithm that we have specified in the attribute, and we compare the hash of the resource with the expected hash that the developer supplied. If they match, we can execute the script. If not, we have to error out because something wrong happened or the developer messed up. So preload plus SRI has a bit of a different story. Like I said, preload is this performance feature where we can load things before we need them in anticipation to speed up the time that we actually do need them later on. And so in this case, the preload request is made, b.com is accessed, and we stuff the resource in the preload cache. This is a renderer-based cache. And then afterwards, sometime later on, when the page actually needs the resource, we fetch the script, and we can match it from the preload cache because it exists. But the first thing we have to do is compare the integrities, right? Whether we got the resource from the network or from the preload cache, we need to compare the expected hash to the hash of the actual resource. But the problem is preload cache entries don't have the raw bytes anymore. We actually throw away the raw bytes after we encode and process the resource. So at this point, it's too late to generate the hash. So we guaranteed mismatch, and then we can never execute that script, and we have to basically say they mismatch, but we don't know why, and go straight to the network and refetch. So this is a lot of pain as well. Preloads are essentially unusable with the normal when the normal resource has the integrity attribute. This is pretty bad because we are implicitly making the developer choose between speed or security. And I think as a platform, we can do better than that. So we came up with a few different solutions over quite a while. And one option was to compute all the possible hashes as early as possible when the preload still has the bytes and before it throws away the bytes. We can store all these hashes and reuse them later. Another option was to just hold on to the raw bytes forever and basically lose the memory optimization that we had of throwing out the bytes early on. And the more sort of web platform straightforward solution was to specify the integrity attribute on preloads so that the developer can supply a given sub-resource integrity on the preloads as well as the main resource. So we did not think that 2 was viable. We had a really good memory optimization of throwing away the raw bytes, and so we weren't really going to budge on this. So we did consider 1, the first option of computing all the hashes at an earlier time. The problem there's several problems with this that kind of ultimately made us go a different route. The supported hash algorithms are expected to grow, and so if we have to change multiple places of the code base to accept, to support all the different hash algorithms, that can incur some technical debt, and the implementers, the original implementers of sub-resource integrity were pretty opposed to this solution. Sub-resource integrity standard is also eventually going to be expanded to not just use like a hash-based comparison method, but also a signature and public key-based approach. And this would further the complexity that we'd have to maintain in multiple places of the implementation. That's just a link to that. And it was just kind of felt slightly hacky. It was ideal in the short term, but a lot of people on the bug tracker were pretty against this solution. So we opted to go with basically specifying the integrity attribute on links. And so kind of what this looks like at a very high level is when we fetch a script, somewhere along the script fetching pipeline, in this case it's in the prepare script method buried in Blake somewhere, we honor the integrity and we eventually fetch the resource and store the expected integrity in the resource. And with preload fetching, we just had to essentially extend the capabilities of preload to include the integrity processing at a later time. And this is kind of where we did it in the pipeline. So this had some nice impact as well. So we, in order to measure the impact, we were trying to estimate the regression that developers would incur, a loading regression, should they use preload and SRI together. So we used web page test for this, and we had a custom version of Chrome that had script preload reuse disabled, and we compared it against one that naturally had it enabled. These are some really high-level rough numbers. If you want the real doc with the more detailed analysis, let me know. But the regressions that we saw initially were that first contentful paint would slow down anywhere between 0.1 and 0.5 seconds on 3G slow speed. The web page test speed index was a little bit more severe, somewhere between 0.3 and 2 seconds. And the load time was a little bit kind of more erratic, but it was generally somewhere between 0.5 and 4 seconds as well, is what we saw for a lot of sites. Basically, we used HTTP archive to find sites that were using a lot of script preloads, and we estimated the loading regression that they would incur. And so there's a lot of future work associated with this. We talked mostly about script today in this presentation. We also extended this to the style destination as well, so preload as script and preload as style. But by spec, there's a lot of other destinations. We have documents, we have font, there's image, there's track. And to extend preload SRI support to all of these different destinations, we decided that it would be best to do a lot of refactoring around how our sub-resource integrity verification is actually carried out. It's a little specific and a bit fragile right now, and so before we extend it, we want to ultimately take care of that, but that's a lower priority. So the next project I worked on this summer revolved around Prefetch and SplitCache. So there's also some complicated terms here, so we're going to kind of go through it slowly, one word at a time. So I just want to start with our motivation as the loading team. So we're the Chrome loading team, and so we care about loading sites fast, but more recently we actually care about loading sites faster than fast. So instant loading has been sort of a core tenet of the team for quite some time now. But we also don't care about certain things, and that's basically everything else. No, that's not true. We care about privacy, we care about a lot more, but the original motivation here for this section is speed, and that kind of brings us to Prefetch. So let's talk about how Prefetch works in the first place. Just give an overview of the mechanics of Prefetch. So again, you're on your cat site, your cats have loaded with no referrer header, they're secure, they're awesome. And the developer of this site anticipates the user to eventually go to b.com. And so in order to create a good experience on the web, we'd like to prefetch b.com to speed that next navigation up. So we access the internet, we pull this resource somewhere in idle time before we actually need it. And basically we stuff it into the cache, under the cache entry with b.com, and then the serialized cache metadata and the response in the table. Later on, when the developer was correct and the user does want to navigate to b.com, we basically first consult the cache. And from the cache, we can see that we do have b.com exist as an entry, and we can immediately use it without ever breaking the internet barrier and swap it in real fast before we even need to touch the internet or do any loading. And so that's sort of the motivation for Prefetch. Now before I continue, I kind of just want to talk a little bit about bananas. So who likes bananas in here? I expect plenty of people. That's a lot of people. That's more than I expected to like bananas. So specifically, I want to talk about potassium. So potassium is like this good substance, right, that we should all keep enough of it in ourselves. I don't know. I'm not a doctor. I don't even know if these numbers are right. But potassium, from the Chromium stance, is actually a renewed set of privacy and security efforts on the web. It's very much an umbrella term. It has everything to do from tracking and cache and resource requesting. But I want to talk about how it affects my team. So the potassium folks, primarily in Cambridge, are interested in partitioning the HTTP cache, which kind of makes our ears perk up because I just showed you that we relied on the cache pretty heavily. And so let's talk about what the HTTP cache looks like. It's basically a hash table with the key being some resource URL and the value being a bunch of serialized cache metadata and the disk cache entry of like the actual bytes of the response as well. So when they talk about partitioning the HTTP cache, it's a little complex, but one easy way to visualize it is that instead of one global table, we actually have multiple partitions associated with a given origin. So in this case, A.com has its own cache table, B.com has its own cache table, and whatever these origins request can be put in only their cache table and no other cache table. And just a fun fact, if they both happen to request the same resource, we would actually duplicate writing this in the response. And I double-checked with the Potassium folks, and we actually don't do any deduplication right now. So just sort of a fun fact here. So let's talk about how Prefetch actually works in a double-keyed cache world, or a partitioned cache world. So we first prefetch B.com like we normally would, go to the network, access the site, but we have to throw it in A.com's cache because we are A.com, and that's what we requested. And so later on, when the user decides to actually navigate to B.com, the security transition in the tab has already taken place at this point. It's already underway. So the only cache we're allowed to access is B.com's cache, which in this scenario is completely empty and does not have the resource that we were looking for. So ultimately, we have to skip the cache and go straight to network, which is unfortunate for a lot of different reasons. This is exactly the kind of thing that makes my team sad, because we care about instant loading. And not only were we not able to load something instantly, but we also were pretty wasteful in the process. So there's a lot of pain here, right? Cross-origin prefetch essentially becomes entirely broken. We can't use it. And we prefetch something that we can never use. And furthermore, we went to the network for it anyway, so we wasted the user's data, their bandwidth, any CPU processing power that we might have incurred by handling that resource, which is a real shame. And this has a lot of impact as well, not just besides making our team sad. So Google Search, in a privacy-preserving way, prefetches those AMP resources on the search engine result page. And it does so in anticipation of the user going to some of them and trying to speed up the next navigation to those resources. These are always cross-origin with the search engine result page because you're going to some other result page that has been hosted on Google Search. And as a result, the next navigations from the SERP page are slower. And when these are slower, Google Search can lose revenue. And when Google Search loses revenue, Google proper loses revenue. And in case this hasn't totally hit home yet, when Google loses revenue, we get less free food. So we all have an inherent motivation to keep cross-origin prefetch working and fast. There you go. So yeah, the goal here, the project was essentially to maintain the performance of cross-origin prefetch, but in a double-key cache world, in a partitioned cache world. So in order to understand how we went about solving this, we have to do somewhat of a deep dive into how partitioning works. So a lot of people, it's really easy to think of a request in Chrome going from Chrome and to the network. But inside Chrome, it's actually a little more complicated, believe it or not. Each request goes through a corresponding, what's called a URL loader factory. And it's actually not even this simple, unfortunately. Everything that comes from a factory goes to the cache. Some hollow cache entry is initialized and written. We go to the network, and when the response comes back, we write this into the cache. But in a double-keyed or in a partitioned cached world, we have multiple tables down here. We don't have one globally accessible table. So how do we know which table we want to access after the factory? So everything that comes from a factory, in this case, has to provide a key. And this key is essentially, and at a very high level, a one-to-one correspondence with a given partition. And so who's responsible for providing the key is a reasonable next question. Is it the factory? Is it the request? Someone in between? So it depends on who the requester is. If we trust the requester and the the requester is considered trusted, we allow them to provide the key if they want, because we believe that they can access whatever cache partition they want because we trust them, so that's good. But if we have an untrusted requester, we actually can't let them provide the key to this transaction, so we have the factory default to a key that all requests going through it will eventually use. So let's talk about how things are loaded in Chrome. So the very first thing we have here, well, first we have 3 processes that you may see spun up anytime, at any given time in Chrome. The middle one here is sort of the boss of everybody. It's the browser process. It's green, so it's trusted, and it's the brains of the operation, hence the brain shape. It can spin up the network service process, which is just this, utility process that takes requests and spits them out to the cache and to the network. But it can also spin up these these renderer processes, which are essentially, and not completely accurately, but at a high level, one-to-one with like a Chrome tab, right? And they're what the user sees. They're everything that runs inside of a tab. Now, we have them red and essentially dead here because they're the only part of Chrome that runs arbitrary application code. So at any given time, from a trust perspective, we have to consider it compromised and trust it as little as possible. So when the renderer goes to make a request, again, we don't trust it, it makes a Mojo IPC call and skips over the browser process. This diagram makes it look like it cuts 2 processes, but it's actually just skipping the browser and going straight to the network service. And again, we don't trust the renderer. So the network service has a factory, and this factory provides a default key for all of these untrusted requests. These are then sent to the network and to the cache and so on. Now, when we make a prefetch, the flow is a little bit different. When the renderer comes across a link rel prefetch, from the renderer's perspective, nothing changes. It makes an IPC call to the browser, and the browser's prefetch URL loader service intercepts this in the browser process. And it spins up something called the prefetch URL loader. And sorry for the nasty visual, but when I saw that Keynote had the intestines shape, I had to figure out a way to work it into the slides. So in this case, the browser process is handling the request, and basically it's just going to forward it to the network service. And remember, this request originally came from this untrusted process, so we haven't assumed any extra trust. The factory in the network service provides a key, and then we go ahead and ship this off to the network or to the cache as normal. So now I think we have enough groundwork to cover our cross-origin prefetch solution and how we were able to get this to work. So we can't just cache every single type of prefetch in a special way, because some cross-origin prefetches might be intended to be used for the current navigation or the current page. So we decided to, at least tentatively, use the as attribute with the value of document as a signal for making cross-origin prefetch be cached in a special way. So when the renderer comes across an as document or main resource cross-origin prefetch, it does what it normally does, and it marks it as such, and it fetches it, sending an IPC call to the browser. The service intercepts this, but the service says, oh wait, hey, I see that this is a request for a cross-origin main resource prefetch. And so we might actually want to end up trusting it so we can cache it specially. So first thing we do is lose Bluetooth connection. Okay, 1 second. Okay. So the first thing we do is make an IPC call to the network service to spin up a new factory. This factory does not have a default key, and it expects all the requests that go through it to provide a key. So the next thing we do is see if we can provide a key as the browser process. We basically analyze the request to determine whether the renderer, because it may be compromised, has tampered with it in any way. And if we decide that it hasn't, we generate a key for it. In this case, the key would correspond to b.com's cache partition. And we pass this to the loader, and the loader basically does what it normally does and passes it to the network service, propagating the key for this request that we've assumed trust over down to the network service, and then this goes, of course, to the cache, and so on. Now, the next requirement we have is that we have to restrict the reuse of these resources to top-level navigation only. This is a really critical thing from a privacy point of view, and was a requirement imposed on us by the Potassium folks. We've just stuffed a resource into an atypical cache partition, and so we have to make sure that it can only be reused in a really restricted way. Now, I'm not going to cover the details of how I did this. It's kind of boring and really technical, but basically it involved an intimate understanding of the state machine that is the HTTP cache. So that was kind of an interesting project. But the end result kind of looks like this, right? You're on your cat site as normal, but you want to prefetch b.com in a very fast way. So you mark it as document because it's a cross-origin main resource. Access the internet. We pull the resource down and we are able to stuff it into the correct cache partition. In this case, it's B. But we also mark in the cache metadata the response as restricted. And so we have to make sure that only special privileged requests from b.com can reuse this restricted request. And so later when a.com attempts to navigate to b.com, we actually send a can use restricted load flag. And the HTTP cache matching algorithm only allows a restricted response to be used by requests with the can use load flag. And these are the only types of requests in Chrome right now that send this flag because they're the only requests that we've considered privileged enough to reuse these types of resources. But, of course, there's more. So we have this idea of recursive prefetches. When the prefetch response comes in, it can actually specify a list of other resources that it would also be helpful to have alongside of it. And so we have to cache these especially as well. So let's just see how a typical prefetch response works. It comes in from the network down to the loader. And basically the loader uses something called its forwarding client and passes it on to the renderer. And the renderer notifies any interested observers and sends it down through what's called the preload helper. Some of these requests may actually require viewport-specific information, so we let the renderer do its thing, and then the renderer basically fetches it as normal. But if we just fetch it as normal, we're going to cache it incorrectly, because it's going to be stuffed into the wrong partition, because it's still being fetched from the wrong origin with the wrong key. So we have to kind of intervene, and the solution we came up with was something similar to this. The prefetch URL loader, instead of just passing this directly to the renderer, it actually propagates it up to the service because we know what key we'd like to use for these recursive prefetches at this time. So what we do is we have a per frame map and we associate unguessable tokens with a network key that corresponds to the cache partition to use. So we store this in our map and we generate this token, we pass it back to the loader, and the loader uses its forwarding client as normal and propagates the request, the response to the renderer. The renderer says, oh, cool, this is a prefetch response, and we've got these recursive prefetch requests to make, so I'll do the same thing, right? Notify the observers, load the request as normal, accessing any viewport-specific information along the way. The only different thing that the renderer does here is essentially propagate this token down through the entire way that the request is made. So eventually, the request is made like normal from the renderer, but with this special token. And so that's what we care about right now. So we have the service intercept this request that has this special unguessable secret token, and the service looks this token up in its map and says, is this an expected token? If it's not, that indicates the renderer could be tampering with the request. We cancel the request immediately. But if it is expected, we basically pull the key from the map and we fetch it like normal. We have the key go to the loader with the request, and the loader ends up fetching it as normal. Using the correct key, in this case, would be with b.com. So we're able to satisfy all the constraints that we had. So yeah, we were able to have the recursive prefetches go through the renderer. Again, this is important for things like image source set and image sizes, like responsive image preloads. And we were able to fetch them with the correct network isolation key, which is a really big win for search. So yeah, the result of this project is we were able to keep cross-origin prefetch actually useful. Same for the recursive prefetches, which is also important for speeding up next navigation processing. We kept Google Search and AMP happy, and we kept the developers happy who use this stuff in the wild. And basically, as a result, we still get free food at Google because we haven't lost enough money yet. This slide is going to be really quick and really technical because there's quite a bit of future work that we'd like to do for this project. It's definitely not finished. One thing we'd like to do is fetch all these prefetches with a unique key, right? Not the correct key corresponding to the correct partition, but a unique key. And that sounds like, oh my gosh, you're just going to undo all the work that you did, right? You're going to throw it into a unique partition and be able to not reuse it. And that's correct. And that's because we don't want to use the HTTP cache to load these resources. Instead, we're going to expand an already existing browser process cache to include the storage and recovery of prefetch requests. So we recover everything from this short-term ephemeral cache in the browser process. So the next section is life in Tokyo, even though there's plenty more projects I'd like to talk about. I just want to cover kind of some of the things that I did while in Japan that were not work-related, and some of the things that I got to see. One of the first things that I did in Tokyo was go to Team Lab Borderless Art Exhibition, or whatever is a long name, but it was really cool. I don't know how many people here have gotten a chance to see it, but it was really a really beautiful thing. It was an incredible exhibition. It took basically the whole day, and I had heard amazing things about it, and so I was really happy to have gotten to see this. Next, I lost Bluetooth connection. Wow, this is awesome. Almost there. Okay. So, I also had some of the best food that I've ever had in my life. I've heard really good things about the food in Tokyo, specifically the beef, like Wagyu and Kobe beef, and I've had a lot of really expensive meats here in Tokyo, and I can confirm that the rumors are true. It's been fantastic. But I've also had some really good pancakes in Tokyo. This is a restaurant called Flippers in Shibuya, and it was awesome. These enormous, thick pancakes that I could only dream about prior to my visit. And they're really, really awesome. Of course, being in Tokyo, I've had some really great sushi as well. This is just a platter of all tuna. Different types of tuna. I think there's four kinds or something like that, if there are even 4 kinds of tuna in the world. So that was really incredible. I also joined the Runners Tokyo group here at Google and met some fantastic people that I got to continue running with throughout the duration of my internship. We went to Nagano for a long weekend and did a running camp. And so this is us at dinner one of the nights. It was a lot of fun. Here's another picture of all of us, and I'm struggling to use chopsticks like I still do today, with Kenji looking nervously into the camera. I also got to celebrate my birthday here in Tokyo, and so the runners group bought me a cake, and we had it after one of our runs. And so that was a lot of fun. This is very good cake. So thank you for all the runners for sort of organizing and taking care of that. One thing that was really special that I got to do, that I had a lot of people telling me to do, and I'm glad that I did it, was climb Mount Fuji. This was an incredible experience. If you haven't done it, I highly recommend it. Definitely, at the very least, you get some good Twitter pictures out of it, like a good Facebook picture or something. It was a really great experience. One thing that surprised me about Tokyo in general was how navigable the public transit was. There's signs everywhere. I don't think I got lost once. To be honest, if you can't figure out where the Kyoto line is from this picture, you got some problems in Tokyo. You're not going to enjoy it. It was really seamless, and I was really surprised how easy I was able to catch on. So the next section, I just want to thank some people that were critical to my success. Of course, you have to start out with the one and only Yutaka. So Yutaka was my primary host this summer, and I could not have. Let's just do that one more time. So I could not have asked for a more patient and intelligent and collaborative host for the summer. It was an absolute amazing pleasure working with you, Yutaka. So thank you for everything and being a phenomenal host. Of course, I have to thank Kinuko as well for inviting me to Tokyo and reviewing lots of my code. Kinuko is a phenomenal engineer as well as a phenomenal manager. She always seems to be thinking one step ahead and is really, really naturally talented at creating a roadmap for the large picture of a project's succession. And so I can only hope that some of that rubs off on me throughout my time here. So the next, I know what you're thinking, this is not actually Kohei. So the next person I have to thank is Kohei. He was my co-host for the first project, the Preload and Subresource Integrity. Kohei I've been working with him since the beginning as well, reviewed a ton of my code. He's gave me an awesome mock interview as well as just being a fantastic support system throughout the summer. So a huge thanks to Kohei as well. Of course, Michael, can't miss out on Michael here. Michael is an incredible manager. I learned a lot from him about running meetings, and the first meeting I ever had with Michael, we went in and we didn't have any agenda. I was like, what's going to happen? Like, oh my gosh. And he just wrote 5 nonsense things on the board, and it all worked out really well. And I couldn't believe it. It was really very interesting. He has a very energetic management style, and I think he's a fantastic leader and a fantastic engineer as well. The best piece of advice Michael gave me this summer was, it seems to be going pretty well. Don't fuck it up at the last second. So, what do you think? Still good?
Yeah.
Okay. Well, there's still a couple days left, so plenty of time. The next person is Matt Falkenhagen. An incredible, amazing thank you for letting me ask you and bombard you with tons of questions every day, especially Mojo IPC related. I had never touched some pretty critical parts of the Chromium code base before my internship. And so Matt was really instrumental in explaining some of these from the ground up. So huge thanks there. So the next is Adam Rice. Adam Rice, in a similar style, extremely helpful for helping me, onboard and kind of ramp up through some of the technical bits of Chrome. Also gave me 2 great technical interviews, mock interviews this summer, and immensely detailed feedback from both of them. So that was really, really helpful. So thank you for being extremely invested in the success of my internship. Of course, Dominic Nicola for first getting me involved in web standards and continuing to work with me ever since. He's been a really great friend and person to know the whole time. Next, I don't know why this slide's here. So anyways, of course, Koharu has been, just has such a warm personality and has been a really great support system throughout this summer. Thank you for being a fantastic recruiter. I guess always looking out for your sheep of interns. Like I said, my internship would certainly not be as successful if it weren't for people like Koharu and Minori as well. So Minori was also critical into my acclimation of Japan. She helped me do things from schedule restaurant reservations to go to the bank and initiate bank transfers and really key things that would have just totally tripped me up in terms of, I guess, society here and HR and just things that I needed to get done. So a huge thanks to Minori as well. Also, can't leave out the intern group as well. Oh wait, what's So sorry, Niels, I didn't mean to exclude you. Okay, so now you're back. Yeah, so the interns have been an equally fantastic support system throughout this summer, and it's been I guess a blast having our bi-weekly intern lunches as well. Here's another picture of us. Oh wait, that's something still on Niels' face there. That's weird. So so here's all of us as Koharu gave us backpacks. I will take the credit for this one for pestering Koharu enough to contact Mountain View and get us some awesome backpacks for the summer. So with that, I want to end with a failed Bluetooth connection. Oh, this is nice. So I want to end on this slide here, okay, with the normal distribution. I think of learning, I guess, a lot in terms of like this kind of curve. The first half you can think of as projects that are maybe too easy, and so your productivity and your learning eventually becomes slightly stunted because the projects are just too in reach. And I think the latter half of this curve you can consider the exact opposite. Things are so difficult or so above your head that you're actually not getting enough done, and you're really not learning as much as you can from them. I feel like almost every project I've worked on with Chrome has been just out of reach enough for me to maximally learn while working on it, but just in reach enough for me to be also maximally productive and be able to actually reap the benefits of those learnings. So I like to consider myself as spending a lot of money on a phone that doesn't work. I'd like to consider myself as spending most of the time in the middle, which has been a really great experience. So thank you to everybody on the Chrome loading team for hosting me and having this be such a fantastic summer. And that's it. So feel free to ask questions or just leave. Thanks. Any questions? Q&A time? People just ready to get some dinner or get out of here? We have free food now that we got Crosswords and Prefetch working. Okay. Oh, yes.
Oh, what was the most difficult thing in your internship?
Most difficult thing during my internship.
Anything is okay.
Yeah, I think what's always really difficult is landing changes in Chrome and then having that cause crashes in the canary population and then having to back them out. Because number one, it's like slightly depressing, and then number two, you actually have to debug the problem and figure that out. And there were a couple changes that I had landed unrelated to the projects, mostly refactoring based stuff that I have done that resulted in this, and kind of digging into those and figuring out what was happening was definitely the toughest thing, but I think that gave me a lot of good debugging experience. Yes?
I have a question about, so there was one slide where it's like you added some kind of like restricted thing to the cache,
Yeah.
And then the website could have a special permission
Mhm.
to grab those restricted items from the cache.
Yes.
And I was wondering how did you decide which requests are privileged enough to do that?
Yes.
Yeah.
Yeah. So basically, the only requests that we were allowed to reuse restricted resources were top-level navigations. So only navigations and not navigations to subframes or nested iframes in a page. This was a requirement imposed on us by the Potassium folks. They said this is the only way that we can let this happen in a privacy-preserving way. And so we basically took the part of the code in Chrome that issues navigation requests and latched on that special can use restricted thing.
So the onus for deciding what's privileged and what's not is on Chrome and not the website.
Oh yeah. Okay, yes. So it's all Chrome internals. The website can't use that flag in any special way. If somehow a compromised renderer were to try and apply that flag to a random request, we actually detect that and cancel it immediately in the network service. So yeah, it only top-level navigation requests from the trusted process can send that. And since it's trusted, we have the belief that nothing is going to tamper that. Is that kind of
Yeah.
So it's a Chrome decision, not a website decision.
The unguessable authentication.
I knew you were gonna. Okay, yes.
Tell us more.
Yes. So we use this class called that's good. Called a base unguessable token, and I meant to look up more about it in anticipation for your question. But the documentation implies that what makes it, that's a pretty strong claim. So what makes it roughly unguessable is that it uses some sort of seed generated at runtime to seed all the unique tokens that are generated with it. So it's nothing static. It's not a key-based thing that's built into the binary. It makes it that much harder for a website to guess. I actually have not looked at the documentation enough to provide what I feel would be a sufficient answer to that question, besides the fact that it uses some special runtime-based memory solution to more cryptographically securely seed the tokens that come from it. So of course nothing's unguessable because it's a finite field and you can just guess something in it if you want, but it's the best we have. Yes?
Having worked on Outlook, Firefox, and Chrome, are there any interesting differences you found in terms of code base or engineering practices?
Yeah, one thing, so I that's a really good question. Yeah, so working on Firefox, I thought the biggest negative I found was that the ramp up time, I guess the barrier for entry was a lot larger. I think there was a lot less documentation. The documentation that did exist was fairly outdated. and the code base had some ancient cruft in a lot of places that were not maintained. I think it made it that much difficult with the tooling to actually ramp up and become a productive developer. I think I was probably more productive in college working on Chrome in my free time than I was at my Mozilla internship, largely because it was such a big barrier for entry for new people, which is really a big shame for a product that strongly relies on external contributors. So I think that was probably the big thing, tooling and documentation.
How about Outlook?
Okay. Next question. Outlook was not good. Outlook was kind of messy. We had just like a ton of random repositories that like some people just didn't have access to, and everything was spread across I feel like half the code base was like seriously being refactored while the other half was like dying, and so like things just didn't really mix well. It was kind of a shame. So it was one of those. It created an environment where the people there for 10 plus years were awesome and just crushing it, and everybody else was sort of like, flying off of like their like coattails, and so that was kind of rough. It was much more difficult to get things going. Another difference, I guess, with Chrome, things are relatively consistent. Like we don't have too many like tests that are like just generally flaky all the time, and builds, like if it's supposed to build, it usually builds. And Outlook was very inconsistent. Tests would fail all the time. Builds might just never build. And there was almost no like incremental build system either. It's just like you make a change and you're done. So yeah. Any other questions? I don't know if there's another event in here or not. I guess we have. Yeah, I just don't know if there's another event, but we could stay all night if you got more questions. Yes.
So it's probably boring for everyone else, but to add the restricted flag, did you have to change the individual cache backends, or was it?
No, so there's basically like a front end. That's a good question. A front end that manages virtually manages the backends, and it essentially serializes all of the load flags in memory and sends them to whatever backend deals with it, and the backend dumps it, and the front end knows how to read everything it knows about from the cache. So as long as the front end knows how to read and write and serialize and deserialize the load flag metadata, then the backend can be completely agnostic to the sort of mechanics. Okay, so with that, I think that's it. Thank you very much, everyone.
3 internships is enough, right? You're done.
Yes, I'm finished. So, do you know where this goes? Or
I know where that goes.
Okay.
I can put that back.
thank you.
Yep.
It's one of the.
Yeah, it went really well.
Yeah, thank you. I'm happy with it.